Let's continue our case study of transition state theory, looking at specifically the case of a bimolecular solution phase reaction. And this time we're going to look and see if we can understand what the activation entropy is. And to do this, we can start off with our equation for the rate constant. We said K is equal to KT over HC e to the minus delta G double dagger over RT. And we can split this once again into an entropy term and an enthalpy term. So we can say if we take the logarithm of K, that's going to be the logarithm of KT over HC. And the exponential, of course, we could say that's going to be minus delta G double dagger over RT. And we could equate that to the Arrhenius expression. So if K is equal to the Arrhenius pre-exponential factor e to the minus EA over RT, we get the log of this expression. We get the log of the pre-exponential factor minus EA over RT. So we've got these two expressions for the log of the equilibrium constant. On the right-hand side, we have this Arrhenius expression, and here is our expression from transition state theory. So let's go ahead and split up delta G into its two parts, delta H and delta S. So we've got the log of KT over HC. And then over here, we've got minus delta H double dagger over RT. And delta G, remember, is delta H minus T delta S. So we get a positive delta S double dagger over R because we have S times T, so that cancels. Okay, so with that much we've done before. So when we equate these, one thing we can do is we can substitute the expression for EA that we got earlier. Earlier, we got that for this type of case study, we got that EA was equal to delta H double dagger, plus RT. And so if we put that in, we get the log of A minus delta H double dagger plus RT, that whole expression over RT. So we can say that's just going to be the log of the Arrhenius pre-exponential factor minus double H double dagger over RT minus 1. Now on this side over here, don't forget, so this was all just the Arrhenius equation, but we plugged in the expression for EA from transition state theory. Over here we've got our transition state theory, and we can say, oh, look at this. Delta H double dagger over RT, delta H dagger over RT, we can add that to both sides to cancel it. So we've got the log of KT over HC plus delta S double dagger over R must be equal to log of the Arrhenius pre-exponential factor minus 1. So all we have to do is solve this for the entropy. So we'll do that on the next page. So we have delta S double dagger over R is equal to the log of the Arrhenius pre-exponential factor minus 1 minus the log of KT over HC. And we could call this minus 1. Let's just put this over here. And let's call this minus the log of 2.71, etc. Of course, the log of that's just equal to 1. Okay, so when we do that, that allows us to combine all these logarithms. So we get the log of, well, on top we've got the one positive thing, which is the Arrhenius pre-exponential factor. We've got this on top, thermal energy kT. And the bottom we have Planck's constant, the standard concentration, and E being 2.71, etc., the natural base of a logarithm. And that's just delta S double dagger over R. So finally, our final expression we get, we have to remember this is applicable only to, or so far we have shown this is applicable to bimolecular solution phase reactions. Okay, so let's go ahead and apply this to an actual case. So if we look at the reaction which we looked at before, which is ethyl bromide reacting in an SN2 reaction with hydroxide to give you ethyl alcohol plus bromide. If you look up the Arrhenius expression for this, we see that the activation energy is 8.9 kilojoules per mole, and the Arrhenius pre-exponential factor for this is equal to 4.3 times 10 to the 11th reciprocal seconds reciprocal molarity. So we said the activation entropy is equal to R times log of A HC over KT E. Okay, great. So let's go ahead and plug that in. So 8.314 joules per mole per Kelvin. And then inside the logarithm, we've got A, which we said was 4.3 times 10 to the 11th reciprocal molarity reciprocal seconds, 10 to the negative 34 joules times seconds, and the standard concentration, which is 1 molar. And then if we divide by KT, we've got 1.38, 10 to the negative 23rd joules per Kelvin. We're doing this at 298 kelvins, and we have E, 2.71, etc. All right, if you plug all that in, we get that delta S double dagger is a negative 30.5 joules per mole per Kelvin. So that implies that the transition state has less entropy than the separated reactants. Okay. Now we have to be a little bit careful because we don't want to envision a transition state and say, oh well, it's this very complicated transition state. Now we have to be careful because this reaction is taking place in solution. So this means the entire system of solvent plus reactants has more entropy than the entire system of solvent plus transition state. But in any case, we can see that when we went up to the transition state, our entropy went down. So not only did we have to pay an enthalpic cost to make a transition state, we also had to pay an entropic cost. So to summarize the stuff we've done, we saw that delta G double dagger for this reaction, this SN2 reaction we saw was 96 kilojoules per mole. Delta H double dagger, the enthalpy cost was a little bit lower. It's 89.5 kilojoules per mole. Oh, actually, it wasn't 89.5, it was 87, wasn't it? Kilojoules per mole. And delta S was a negative, let's round up and call it negative 31 joules per mole per Kelvin. So the discrepancy between these two, the reason why this is more unfavorable than this is because we have this additional enthalpic penalty, or entropic penalty rather, that we have to pay to make the transition state in this reaction. So In summary, we can find the difference in entropy, the difference in enthalpy, and the difference in free energy between the reactants and the transition state for any reaction as long as we have the Arrhenius parameters. So as long as we have the temperature dependence of a reaction, we can get the Arrhenius parameters, the activation energy, and the pre-exponential factor, and from them we can get delta G, delta H, and delta S double dagger.